Hi everyone, thanks for joining for this week of our short training series. Today we're going to look at process considerations for cored sandwich parts. So we'll just have a brief introduction of the presenters, quick intro to Convergent, and then we'll get into the meat with the case study of the sandwich sections, and then we'll follow that with a question and answer period. So if you have any questions at the end, you can type them into the chat window and send them to the host on the WebEx session, and then we'll filter through the questions and answer them the best we can. So myself, Nick Cecchini, I'm an analysis engineer in the analysis applications group at Convergent. And then the main presenter will be Alistair McKee, who's the engineering lead of the analysis applications group. So at Convergent, if you've been into the other presentations, you've probably seen this before, but we provide a lot of engineering services like training and education, as well as consulting on specific process analysis and design projects. We also do thorough material characterization. We provide and sell coho hardware, which is for gas flow and vacuum leak detection. And then we also have a suite of software for process simulation. So we'll be looking at today using Raven, and then we also have Compro, which is a plug-in into finite element solvers, and LIMS, which is for simulating the 3D mold filling. We have quite a few partners and customers, so these selected partners and customers are in the academic and research areas, and there's a long list of them. As well, we have software partners, which we, as I said, have software that plugs into these different softwares. And then we have, quite a few industrial customers and partners that we team up with on projects and large industrial projects. So as I said, this week we're looking at optimizing the thermal processing of sandwich panels and sandwich parts with Raven. And Alistair is going to take over now and run through this portion of the presentation.
All right, thanks, Nick. So I'm going to start off with a little bit of background into what a sandwich panel is, just to make sure everybody knows what we're talking about. So really it's a thin, stiff structural layer bonded on top of a relatively thick, low-density core. And you might wonder, why do people go to the trouble of adding this complexity to a structure? And it's usually with the goal of increasing the bending stiffness, but without adding significant amounts of weight. And so you put the structural portions where you need them, and you have a portion in the middle which will give you that bending stiffness that you need. And so this is used in a lot of different industries, but particularly aerospace, automotive, marine applications. We see this a lot using composite materials, and particularly carbon fiber and fiberglass reinforced polymers. You will also see it in other industries where it's with aluminum or other metallic skins and various applications. And so today we're going to focus on the composite as the structural layer as well. And mostly we'll be talking about honeycomb core, but also foam as possible. In this particular application, there's often a film adhesive applied as well in between those two, actually as the bond layer. And you can see a few examples here, just of a thick section here, and here's usually how they finish off the edges with a bit of a taper. And when we're talking about processing of composites, we always have to think about what are the goals and what's driving what we're trying to do. So there's usually very specific material and process specifications This is especially true in aerospace, but other industries will have these as well. And so these will often specify maximum, minimum heating rates, max temperatures, hold times, the pressure cycle, all various things can be specified from all of that. But you might also have some part-specific requirements. So particularly honeycomb cores, they might have a pressure limit. So you may actually not be able to go as high of pressure because you'll actually crush that core because it's a low density and relatively low strength material. And there's other considerations, for example, intermediate holds to increase resin flow might get used. And then with any process, usually there's a driver which you're trying to optimize the process, which would be something like cycle time, but also maybe compatibility with processing other parts all at the same time in kind of a batch or bus stop loading scenario. There's various other ones that we consider with all of these. The main one we're going to focus on a bit of is really the thermal stuff today. So when we're talking about thermal, we're usually looking at a cure cycle that's applied to the part. And so this would be in an oven or an autoclave or maybe a heated mold. And so this is the air temperature that we're applying, or actually the tool temperature might be like from platens in a press. And usually to be an acceptable part at the end, you would need to follow some kind of prescribed cure cycle. So in here, I'm showing just an example, MRCC, manufacturer's recommended cure cycle, with the average in the middle here, and then upper lower bound that might be specified on a data sheet, for example. And every manufacturer will also have their own specific requirements around this that they've come up with as well to further bound this. And just to make sure we're sort of bounding this back or relating this back to sort of real world parts, I had a few example part families that we often see in composites. So a sandwich structure here, this is landing gear doors where they've got these big sandwich panel portions with some pad ups on them as well for connection points. This is what we're actually going to talk about today. But we also have skin with stringers as an example as well, a typical type of part. And then maybe a skin with some, not stringers specifically, but thicker sections as well as localized reinforcements. And what I'm going to present today is the idea of how do we break this complex part down into this idea of 1D zones of common response. So I'm going to use an example, which is this sandwich structure here, and we're going to look a little bit deeper at this particular case here. So this idea of zoning is where we're actually taking a 1D drill through of a composite part, and we're going to look at common through thickness profiles here. So in this case, we see there's 4 zones, one where there's no core, where there's a thicker core, one section, this is the pad-up section where there's a thicker laminate on top, and then there's another little step down here. And one of the nice things about composite parts in particular is that it's actually often a very good assumption to make a 1D heat flow analysis of this. That's because they often, if they're long and thin, this is of course a compressed version, so I can show it in a schematic. It's not really to scale. And often most of the heat transfer is coming from the top and bottom, and so this is really a good approximation here. And so we do actually have to make a few assumptions about this. Really is that there's no heat flow in or out of the sides, and so this is true except for when you come right up to the edges. And so that is a one consideration where it would that assumption starts to break down. And then the other thing that we're assuming here is that we have a uniform heat transfer throughout the cycle. That's a limitation right now in Raven, where we can only apply a single HTC, which is the effective heat transfer coefficient at the top and bottom of a stack up. But we're reasonably comfortable with that as an assumption, and this really will let you bound a problem. And so when you do this idea of zoning common response zones, it's a very good first approximation of many composite parts. So what I'm going to do here is set up how we would actually go through this in a Raven analysis. And so, as I mentioned, the top laminate actually does vary slightly in thickness here. So zone 3 particularly is a little bit thicker, And the honeycomb core thickness also has a little step down here. And so we'll go through the examples here. And what I've done actually is pre-set up these runs in Raven. And so the inputs that I'm using here, these are the different thicknesses, actually these are boundary conditions, so these are the heat transfer coefficients that I was using in the table here. But particularly what I've highlighted is the lines that are changing in this. And so we're actually making a reasonably complex setup here. This is pretty typical, where we have a boundary and then we've got some breather on top. We've got the laminate. I've included the film adhesive that we use here and a core material where applicable in these cases, some additional film adhesive, another laminate, and then the actual tool. We're using an Invar 36 tool in this case. And what I'm going to do is actually run through these constraints here, or sorry, these examples, and then I'm particularly looking at peak temperature. So I've just defined a 185 degrees Celsius as a max peak exotherm or peak temperature here. We're going to take a look at particularly the laminate. Now, of course, if you're curing the film adhesive, you should look at that as well. It's so thin in this case that it's not driving the problem here, so we've left it out. And there are many other requirements that you can apply here: heating rates, max lead and lag, the differential of part lead and lag temperatures. There's various things, soak times and hold times. These can all be applied, but for the interest of time, I've just looked at peak temperature, and that's really what would probably drive this problem initially. And so what I've done actually is set these up so that I can run these in Raven here, and I'm going to go to this sort of dual mode, so hopefully you can see everything okay. And what I've done is set up these 1D drill through zones. So just as we had there, I've got zone 1 through 4. And what I'm going to do is open up one of these so we can take a look at it. So what I've done is define the stack up here, just using those dimensions that we had here. And so zone 1, it's got the heat transfer coefficient at the top here, 40 watts per meter squared Kelvin. And we've got a slightly lower one on the bottom. That's pretty typical, with a little bit of restriction from a frame on the tool itself. This is typical of an autoclave, medium airflow would get you something around this range here. And what I've done is put in breather. I've chosen this out of our open material database. I've used XL8552 resin. It's a plain weave fabric in this case, and applied also film adhesive in the middle. And so this is the zone where we had no no core, and so I've just got a film adhesive layer in the middle. But you could also potentially leave that out if that's not actually how the part is being built. In the composite here, and the Invar tool as well applied. And when I run this, it'll run through here, and we'll get a plot that looks something like this. I've actually hidden several of the items on here, so we actually get a full through thickness profile of all the different items in the stack up here. But I've hidden the breather cloth because it's actually not curing and we're not really concerned about it. I've actually hidden the adhesive layers because they're not really going to drive this problem, and the Invar tool as well. And so by default, Raven will give you all of those through thickness profiles. And just for clarity, I've hidden several of these here. Put the bottom one back on. And so we ran through and run all of these different scenarios with the different stack ups. And what you see right away is as soon as we add this core, we have an issue where there is actually a peak exotherm that is coming up quite a bit above the hold temperature here. We actually hit the temperature that we specified at 185 C. So that's maybe a bit of a red flag. And then zone 3, we see this as well. This is clearly going to fail our specification in this case. Zone 4, back within sort of a normal bound. So I'm going to jump back here to the presentation because I've summarized those same plots. I actually probed both the upper and lower laminate in this case, and so you'll see that the lower laminate never really has an issue, but the upper laminate, in particular zone 3, this is that very thick pad up region. We have a big exotherm, and we're going to need to look at ways to optimize the process to get around that. So I filled those in here, and this is something you can typically do with Raven is have a criteria and then use Raven to do the analysis and fill in what, for example, for this part, what would be happening in these different zones. So I've highlighted, I would be concerned by exactly hitting the peak by zone 2 and very much so by zone 3. This is particularly an issue. And so this really comes down to a thermal management problem. And so we have various strategies to try to address this. And so I'm going to give just a bit of background here on what we could possibly do. In this example, the upper skin is actually very well insulated. It's both by the low conductivity core and the breather on top. Those are both providing insulation. And I've shown here actually this is zone 3 where the laminate is a little thicker on top versus on the bottom. And so when the reaction kicks off in the part, you end up with this exothermic response, and the bottom layer is actually able to transfer heat out into the tool, but the top layer has nowhere for that heat to go, and it starts to build up inside. And that's really what is driving this issue here, where we're going to have potentially heat damage and a failure to meet the specification. And so strategy number 1, this is probably what most people would think of right away, is that we can change the cure cycle. And usually it doesn't, you can't change the cure cycle wildly, but you may be able to work within the bounds. And so, for example, here, a slower heating rate is something that you can prescribe. And this will often provide a way to lower the reaction rate and potentially get some of that heat out earlier at a lower temperature so you don't miss the specification. So I'm going to actually go back to Raven here and see if we can go ahead and do that. So zone 3 is what is driving the problem here. And so I'm going to actually go in and modify the cure cycle here. And so I can open up my thermal simulation. What I've chosen was just the average default cycle here. This is the average for 8552 from the data sheet. It's the US data sheet in this case as well. So they also have prescribed some other cure cycles here, and so I'm going to use the slow cure cycle just as an example. And this just has lower ramp rates overall. And this is, we're going to see what the effect is here. And so if you recall, we had a peak temperature of about 210 C. So I'm going to let this run now here. And we're going to see what the new peak temperature is just by reducing the ramp rate. The big problem that we're going to see is that we have a penalty on the time as well. And so we've added almost 100 minutes here, but we have brought that maximum down. It's still not within the specification limit, but it has brought it down a little bit here. So if I come back here, this is the same plot we had just generated there, but essentially I've lowered this by about 6 degrees. However, we've added 100 minutes to this cure cycle, and that's not good, but more importantly, it still doesn't meet the specification, and so that's actually a bigger problem here. So you say, what other strategies can we employ here to potentially get this part through? And so in the pad-up region, it's possible to actually pre-cure an insert, and this is really to reduce the exothermic potential. And so this insert would be made from the same material as the top laminate, so it's 8552 plain weave fabric, and you would surround it in uncured material to achieve the desired thickness. Now, these pad-up regions are often sacrificial. They'll get machined afterwards. They're also really simple in shape and geometry often, and so it's actually relatively easy to make this part separately and then place them in there. So we're going to go back into Raven here as well. And what I'm going to do is actually change the cure cycle. So zone 3 is still the one that is driving this. I'm going to change us back to the default cure cycle, so we're not adding additional time. But I'm actually also going to break up what we have here is the 6 millimeter thicker region. And I'm going to do so by adding 2 more materials to the stack here. So if I select this area here, I'm going to add a material and add a material. And Raven will default to the top material in the list here. But I'm going to come down and pick out this 8552 plain weave fabric. and do the same thing here with this material. So we've added 2 more pieces to the stack up. And I want the overall thickness to be the same as what I started with, which was actually 6 millimeters. And so I'm going to actually go with 1 millimeter on top, 4 would be the pre-cured insert, and then 1 millimeter on the bottom. And then the last thing that we can do here is you can see the initial degree of cure, and we can actually set this up to be something that, to be a pre-cured insert in this case. And so I actually pre-ran just a 0D analysis with the default cure cycle. That actually gets you to 0.88 final degree of cure after that. So I'm going to use that as my assumption here. You could put in 1, I'm going to put in 0.88 to be somewhat realistic, and this would really be, you could pre-cure this part, you could even partially cure the insert and check and see. But in this case here, I know that the initial degree of cure is going to be about 0.88%. And now we can actually run this and then see, so I've gone back to the the default cure cycle, which is the 300-minute cycle, and now I've reduced, potentially reduced the exothermic reaction by adding this insert, and we'll see what happens here. So because I've added a few different pieces into this stack up here, we'll see that the plot, Raven has automatically added a separate little section for each one of these. So I'm going to actually turn on, I got to turn off a few other things in here. This is the tool, and so there we go. We've got the full top laminate. And what you can see here is that I'm actually going to hide the legend, that maximum exotherm that we were at, well over 200 still, has now come down to a very, very small, right around the whole temperature. And so this would pass quite easily. So if I jump back here into the presentation, you can see I just did an overlay of exactly that. And so now we're reducing that peak exotherm by 30 degrees here. No additional cure time was required to meet this, to actually make this part successfully. However, you do need to pre-cure those inserts, although that can be done quite easily. And more importantly, it meets the specification requirements in this case. So really, in summary, sandwich panels have these unique properties because they're actually separating the laminate, and you potentially move that top laminate into an insulated zone, and this can cause problems with exotherms in particular. And there's various other process upsets that can be introduced as well, but particularly pad-up regions they're very susceptible to this. Slower heating rates is an option that we have here. We saw that it did reduce the potential, but it does add processing time. And then pre-cured inserts we saw as actually a really effective way without modifications to the cure cycle. And in this case, you may actually need to do both to get all of the zones to match up, and because we didn't actually look back at zone 2, where we would probably not do a pre-cured insert. However, in that case, you may go to a slightly slower cure cycle to get that exotherm below 185 with a comfortable margin. And really, what we saw today, that idea of zoning and using 1D drill throughs is a really good way to break up a complex part and do the analysis in a simple, fast, and easy way. Raven really provides that platform to do so without needing to be a finite element expert. And you can see with the complex stack-ups that I created there, and modifying them is pretty straightforward, and so you can add many curing and non-curing materials throughout. And it's a really great way to assess the thermal management strategies that you might want to employ, really gauge their effectiveness. And there are many different scenarios that you can go through using that analysis type. So that's actually the end of the presentation at this point, and so we've got a bit of extra time today for Q&A, and so I hope you can type in questions if there was any coming in. Nick will be triaging them here, and then feel free now to type any questions that you have in. You can also email them to info@Convergent because we have somebody monitoring that. We'll have a few minutes here for Q&A.
Okay, so we have our first question here, and it is, how do we deal with tapered edge of a honeycomb core?
Right, okay. So I'm going to actually go back up to the start of the presentation where I had that picture of the honeycomb core here. So I guess this is really how would you address this zone on a real part, which would typically taper down like this. And so ultimately, we don't actually address that in the 1D analysis. It's actually one of the areas that we are assuming that we're far away from this area. And so because the cross-section is not consistent, you can't make that simple 1D drill through, and the 1D assumptions really break down. You do actually have heat transfer and different conditions happening here. However, what we were looking at was the zone up on the top here, before that taper, and the zone down at the bottom here. And so when we parse the problem and break it up into these two zones, we're really bounding the problem. And so we can see is that if we have a problem in the thick zone, then we need to address that. But if we're safe in that thicker zone and safe in the thin zone, we should be fine everywhere in between. And if you do have a complex part that does have many different shapes like this, we also, Convergent has a tool for that, and that's really Compro, and you go to a full 3D simulation. It does complicate it a little bit, but it's entirely possible to simulate the entire part with all the tapers and everything.
Great. Okay, we have another question here. What about adding an additional intermediate dwell?
And sure, absolutely. If, for example, in the zone 2 where we were getting close to the max temperature there, 185 C, we would probably need to do some modification to this cure cycle to make sure that zone passes. And so in that case, I had gone through using a lower ramp rate, but another strategy absolutely would be to put in another dwell to try to dump a little bit of the heat and to ensure that no part goes over over the maximum temperature that was specified.
Okay. Another question here, instead of honeycomb core, can we use foam core?
And so absolutely. Now, we don't have any foam cores in our open database within Raven right now, but since most foams are non-curing materials, you can typically get the properties off of a data sheet, and you can actually create a material file for that. There's actually a tool within Raven now, it's the material manager. I'll bring Raven up again briefly here within the menu, and here you can actually create a new material. In this case, you would create a composite material and then apply the properties at the composite level, or potentially matrix and apply them 100% matrix with no fiber.
Okay, the last question to come through is it okay to assume that all the materials in the stack are pre-cured when you run the simulations?
And so, yeah, you can actually adjust the initial degree of cure to any value that you want in there, and so you can actually show, you can even run this in a simulation with no curing materials in there and use this tool to do that analysis. And so you can look at putting pre-cured sections in wherever you want, or even a partially cured section wherever you want in the stack up, and Raven's able to deal with that without any problems. one of the things that you do run into if you do put in uncured sections, for example, if you didn't have a cure kinetics model, is that you will not get that exothermic response, and so you won't be gaining that extra knowledge that we were really seeing here and getting out of the simulation.
Okay, great. So those are all the questions that came through. If anyone wants to send any more, and now we can wait, but if you have any more questions, like Alistair said after this, please send it to info@convergent.ca.
Right, and our next webinar coming up next month will actually be talking about assessing process-induced deformations with Compro.
Great. All right. Okay, I think that's it. If no one has any more questions, we can end it here, and then we'll look forward to seeing everyone next month for the next webinar. All right, thank you, everyone.